Hello explorers and welcome to another video. Today we are doing the Advent of Code puzzle. The Git repository is linked in the description below, and if you want to see all of my trials and tribulations, you can see the full recording as a member of this channel. Day 15, Beacon Exclusion Zone. You feel free. Feel the ground rumble again, and the distress signal leads you to a large network of subterranean tunnels. You don't have time to search them all, but you don't need to. Your pack contains a set of deployable sensors that can imagine where they were originally built to locate lost elves. The sensors aren't very powerful, but that's okay. Your handheld device indicates that you are close enough to the source of the distress signal to use them. You pull the emergency sensor system out of your pack, hit the big button on top, and the sensors zoom off down the tunnels. Once the sensor finds a spot it thinks gives a good reading, it attaches itself to a hard surface and begins monitoring the nearest signal source, beacon. Sensors and beacons always exist and at integer coordinates. Each sensor knows its own position and can determine the position of a beacon precisely. However, sensors can only lock on to the beacon closest to the sensor and measure the Manhattan distance. There is never a tie where two beacons are the same distance to a sensor. It doesn't take long for the sensors to report back with their position and the closest beacon, your puzzle input, for example. And here we have a bunch of beacons. To consider the sensor to 18, the closest beacon to it is minus 215. For the sensor at 916, the closest beacon to it is 1016. Draw the sensors at S and drawing the sensor as S and beacons as B. The above arrangement sensors looks like this. This isn't necessarily a comprehensive map, all beacons in the area though, because each sensor only identifies the closest beacon. If a sensor detects a beacon, you know where there are no other beacons that are close or closer to that sensor. There could still be beacons that just happens not to be close to a beacon or to a sensor. Consider the sensor at 87. This sensor's closest beacon is 210. So you know there are no beacons that are close or closer in any position at none of the detected beacons seems to be producing the distress signal. It isn't for now keeping things simple by counting the positions where a beacon cannot possibly be along a single row. So suppose you have an arrangement of beacons and sensors like in the example above, and just in the row where Y10 you like to count the number of positions a beacon cannot possibly exist. Coverage all sensors that looks like this. In the example, the row where Y10 there are 26 positions where a beacon cannot be present. Consult the report for the sensors just deployed in the row where Y is 2 million. How many positions cannot contain a beacon? First off, we need to parse these, but that shouldn't be that hard. And then I want to figure out what is the actual range sensors can be at. So the smallest and largest positions of them. And that is our line pretty much. And then we need to figure out the Manhattan distance and add that to that minimum in order to figure out how long the line can be, and then from there work out on that line which sensors actually have a Manhattan distance that is shorter to that position on that line. So let's start by parsing. So let's say that we have a list of sensors. Equal to new array list. So there is our list of sensors, and here we can take sensors, add new sensor line. So that is our current thing, and we will create a sensor in our package here. And a sensor is created by this line. So that is something that we know, and it has an X position. So that is one thing. We don't need to know where the beacon is. We only need to know the Manhattan distance. So those are the things that we need to know. So we will have this private static pattern sensor pattern compile, and here we want to have this full line like that, and then we want to have something here which could be a digit or a minus, and we want multiple of that. So we want a bunch of these values here. So that is our pattern. Maybe we could put that on a new line so it's a little bit more readable. So here we have a sensor pattern. Matcher is line like that, and then we get a matcher, and if the matcher finds this, then we will take the group 1 integer parse int group 1 into x, next into y, and then man x and man y. Or we can take beacon x beacon x, beacon y. And then we want the Manhattan distance to be equal to math absolute of x minus beacon x plus math absolute of y minus beacon y. So now we have a bunch of Manhattan distances. We have a related problem here. What is that? The list is not defined, but now it is. So now we have a bunch of sensors. Hopefully they are correctly. So now we have a bunch of sensors. And then we want the sensors min x and max x. Public int min x, and that would be x minus Manhattan. That would be minimum x, minimum y. We don't need. We will need max x. Max x would be Manhattan, x plus Manhattan. So those are the minimum and maximum. So if we for loop through the sensors, min x, let's say integer max value, and then int max x is equal to 0, and then we take min x is equal to math min of sensor min x and min x, and then we do the same for max. So now we should have a minimum and maximum x that we need to loop through. Min x minus 8 to 28. Okay. So if for a loop of x is equal to min x, and then x smaller than max x, can do +1 and -1 here. It doesn't really matter if you do a little bit extra. And then we loop through the sensors. And if the sensor is have a close, shorter Manhattan distance, shorter Manhattan to x, y, and here we want to say that y is equal to 10, but y could also be equal to 2 million. I think we could do it like that, just for ease. So if this is true, then we want to count it. So we want to counter here. That is 0. So now we want to count how many things are on that line. And down here we want to print that count. So here we want to take this x minus x and math absolute that plus math absolute this y minus y, and that, if that is shorter than Manhattan, that is what we return here. So if we run this, what do we get? We get 24, and the result should be what? 26. Okay, so we are close. So do like this then. Out, print, and then we print a dot. Else we print a hash mark. Let's see what we get. Okay. So we actually need to break here because we don't want to count it twice. Then we get 23. If we do equal to here, then we get 27, which is very close. So Boolean found equal to false. So we do that there. Found equal to true. And then we do system out print, and here we take found print hash mark else print dot. So let's see what we get. We get this one. And if we do less than Manhattan, what do we get then? We get that. And what we want. Online x, y. So if that is true, then skip or continue on the main. Here we have the main. So the main loop will continue if it's on the line. So if return x equal to x, so this x is equal to x, and this y is equal to y. Then we also need to have a dot printed here, if that is the case. But it's not the case there, and I guess it's not the case here either. Or is it the beacon that is on line 10? We have a bunch of beacons on line 10. So that's a complication as well, because a beacon cannot be where it is. So, Jesus. So we need to keep track of the beacons as well, just to figure out if... okay. So here we say private int beacon x beacon y. We'll do it like that, and then we remove these, so we actually have those, and then we check beacon x beacon y. So now the beacons can't be on that line. And then we get 26. Switch it up and try the larger sample set here. Huge number here. So 5 million something is the positions that are not counted on that line, where a beacon cannot be. So let's see if that is correct. Yes, you get a gold star, I get a gold star, everybody gets a gold star. So let's go to part 2. Your handheld device indicates that the distress signal is coming from a beacon nearby. The distress beacon is not detected by any sensor, but the distress beacon must have XY coordinates no lower than 0 and no larger than 4 million. So to isolate the distress signal, you need to determine its tuning frequency, which you can be found by multiplying X coordinate by 4 million and the Y coordinate. In this example above, the search space is smaller. Instead, the X and Y coordinates can each be at most 20. With this reduced search area, there is only a single position that could have a beacon, 1411. The tuning frequencies for this beacon is that 1411. Find the possible position for distress beacon. What is the tuning frequency? Find the only possible position for the distress beacon. What is the tuning frequency? The distress beacon is not detected by any sensor, but the distress beacon must have an X and Y coordinates, each no lower than 0 and no larger than 4 million. To isolate the distress beacon signal, you need to determine its tuning frequency, which can be found by multiplying X coordinate by and adding Y coordinate. In this example above, the search space is smaller, so can be at most 20. Okay, so then we got that. So here we should be able to have an x minus 20, x plus plus, or x minus 21. And then we do the same for y. And then we should have the similar thing here to check all main 2, so that is not a possible. And here we just do a break. So we don't want to find it anywhere here. So here we can have this found. So if not found, then we will do a system or print out here x y. So if we run that, not on the large example of course, we need to run it on the smaller one. So we don't continue there. And then we do, what did we do? We do x multiplied by 4 million plus y. Was that the correct one? X, yeah, plus y. So then we get that value. Okay. Here we can do Mike's value 21. So that's the max value of that. Now that we want to run the larger example here, we want a max value of 4 million. So that could take a while. So maybe there is a better way to do this. So we do that. We do a multi-runner. And that would be extend runnable, like that. And we have a run function, and the multi-runner would take a y coordinate. This y is equal to y. Private static int y. Private int y. There we go. And here we will do a run. So run is this. Pretty much. Where we have y, y. Yeah, private list of sensors. That, of course, we need to have. We have a list. And we also need the max value. So let's hard code that here. Million, like that. And here we just do break, because we didn't, you found a sensor. Continue main 2. So we actually have a bug in the original code. Because it's that one I won't continue. Okay. So we can stop this one. There we just do a return. Implements run above, yeah, of course. So now we have a multi-runner that can run each line. Executor service, yes. Executor service, executors. Fixed thread pool, 12, no. Let's do 10. Yes. Submit task. New multi-runner, sensors, Y1. Like that. And then we comment this stuff out. Yeah, we just wait. And we are back. And this is a little bit scary because I actually had to stop this running in order to record because it took so much CPU. And I've done some small changes off camera, not much. So this was what we had before, this running through a bunch of values. I changed it up so I actually run it through thread pool runner with 10 threads, so 10 values at a time. I created this multi-runner where I put in the sensors. And this multi-runner pretty much takes the sensor and one Y coordinate that it needs to check. Then it will run through all those. Let's see, I need to copy these values just to be sure that I don't lose them. I can't stop thinking about it. So it will actually, before it runs, sort the sensor with the shortest distance to Y for the current sensor. So I actually have them closer to the value that I want to find. And then I can go through all of them and see if, is it on the same line? Or is it this specific coordinate, this sensor? Or is the Manhattan's distance shorter? And if so, I just continue. That is not the correct one. But if I find one, then I will print it out here. So, and I also have this function that runs prints out a dot every 1000 Y. So if I've cleared one that is the thousandth runner, it will draw a dot. So after about 1 million tested values from the back, I actually found these coordinates. And because I calculated with an int, I get the totally wrong number of minus something. So what I want to do now is, at the beginning of this main function, have a system exit of status 0, and then system out print line this value times 4 million plus this value. That is what it should count. So xy, 4 million times, can do like this. So that should be the exact same. What does it say here? So if I run this, what do I get? Should get a huge number. I still get that. So long values of all of these. Can it handle that? Yeah, so then I get a very large number. So this is possibly the correct answer to the actual question. Very exciting. Let's put it in. If it isn't, we have no clue because this is really hard to actually find. Yes, you get a gold star. I get a gold star. Everybody gets a gold star. So we found the solution to part 2. So this is of course not a really good solution. I brute forced through this in order to find the correct solution for this part. It took a long time. It had to run with multiple CPU cores and so on. So I'm very excited that I had it right and that I actually found a solution. If you have a better solution, please leave some code down below so I actually can see how you should solve this. If you like this video, give it a like, share it with your friends and colleagues. If you haven't subscribed yet, please do that. And I really hope to see you in the next video.